Hello and welcome to my talk on aging for the stationary KPZ equation. It is based on a joint paper with Jean-Dominique Deutschel and Gregorio Moreno-Flores, and you can find the paper on the archive. Aging is a property of dynamical systems which are out of equilibrium. Examples include the Sinai walk, trap models, spin glasses, and more recently, the KPZ equation in the narrow wedge regime. Today we are going to deal with stationary KPZ and EDWARDS-WILKINSON models. Roughly speaking, a system is satisfying aging if the older it gets, it relaxes in a slower manner. There is a canonical formulation in terms of correlations of the process in two different time points as time goes to infinity. More formally, you say that the process is satisfying aging if you compare the correlations of the process in two different time points with a fixed ratio A, then they converge as time goes to infinity to a certain function of A, which is strictly between 0 and 1, as long as A is strictly larger than 1. And then this is called the aging function of the model. This is a non-trivial property, and you can easily convince yourself that if you take some non-trivial finite state Markov chain, then the correlations are going to converge always to either 0 or 1. Our discussions on the aging problem for KPZ started from a conjecture in this paper by our co-author Jean-Dominique Deutschel together with Amir Dembo, where they considered the semi-discrete equation, the following, and they proved that in dimension 1 and 2, whenever capital F is either constant or a square root, then you see aging, and whenever it is linear, then you see no aging. However, they conjecture that still in the linear case, if you take the logarithm of the solution, then you should see aging in dimension 1 or in a logarithmic time scale in dimension 2 also. There are also non-rigorous predictions for correlations of stationary KPZ in these two papers. And in Ferrari-Spon paper, the Ferrari-Spon paper here, there is an exact prediction of what should be the time-time correlation scaling function, namely the aging function, that we verified in this work, and I'm going to discuss it in a minute or two. There are other non-rigorous and experimental works in this direction, and some rigorous results in this direction. Particularly, I want to mention this work by Corwin, Goshal, and Amon, that they considered KPZ equation, the narrow wedge initial data, in the KPZ fixed point scaling, and they managed to identify the rates of the time-time correlation function. In this paper, they have a section with a nice discussion on time-time correlation and aging, and they mention all of these references and others. Today, for us, we're going to deal with stationary KPZ equation in one dimension, and we are going to talk about the Cole-Hopf solution, meaning that if you start from the stochastic heat equation, so here it is, this is a space-time white noise, in the stationary regime, meaning that you start from the exponent of a two-sided Brownian motion, then it is well-defined, and it has this form, this mild solution. And now if you take the capital H to be the logarithm of the solution, then this process is called the Cole-Hopf solution to the stationary KPZ equation. Here it is, and if you want to read more about it, you can consult these papers. Two-sided Brownian motion is indeed stationary for KPZ, and it was proven in these papers. And what it means is that if you consider the law of the space increments of the KPZ, then it is independent of time. Okay, so if you write time t here or time 0, the increments, they have the same law as the process. And this, since this is two-sided Brownian motion, this is actually also independent of y, right? The law of that. So as a process, it has the law of a two-sided Brownian motion. And the first observation here that we have is that you don't have just space increments that are stationary, but actually space-time stationarity, meaning that you can start not just from a certain position, y, but also from a certain time, s, and when you take the increments, it has the same law as if s and y were 0, okay, as a process. So when you have this, an immediate corollary is that you can reduce the space-time covariances to variances only in this form. And the result, the corollary of that, is that then you have aging for the stationary KPZ equation. Namely, if you take x and y in R as positions, and you compare the correlation of the process in these positions with times that have a fixed ratio A, and you take time to infinity, then this will converge to a function psi KPZ of A, which is strictly between 0 and 1, and moreover this function has this explicit form. So you see here the scaling of the KPZ in the definition, and the proof is relying on this covariance to variance reduction that we had together with the convergence of the variances, which is a special case of a paper by Corwin and Gauchal. And it is interesting to see what happens when you don't take just position to 0, but you take it to infinity together with d, like that. This is the 3 to 1 scaling, and this is, of course, is leading to the KPZ fixed point, which is widely open. You don't know that you have it. Particularly, you don't know that you have the space-time correlation convergence here. You do know that in the KPZ fixed point, this is scaling invariant. So it has the 3 to 1 scaling. So we have actually equality here when this is the KPZ fixed point. What we know is that the KPZ fixed point is also satisfying aging with the same aging function, of course. And you have a certain explicit function of the space-time correlations of the fixed point in terms of variances only, as explicit as it can be. Okay. We also consider other models, so semi-discrete models, in particular the stationary O'Connell-Yor model. So if this is the partition function of the semi-discrete directed polymers in Brownian environment, started from the exponent of a Brownian motion, then a result by our co-author Gregorio Moreno-Flores, together with Castel and Remenick, and another paper with Ara, is that properly rescaled in this intermediate disorder regime, it converges to the stationary stochastic heat equation. And what we proved here is that now if you take the logarithm of this rescaled partition function, then it satisfies aging in some form, meaning after you take n to infinity. Okay, then you need to take t to infinity. We prove also similar results for asymmetric exclusion process and last passage percolation in the stationary regimes. As a comparison, we consider the Edwards-Wilkinson class, namely the Edwards-Wilkinson equation here in the stationary case, meaning starting from two-sided Brownian motion, and we prove the similar aging result. So this is the aging function of the Edwards-Wilkinson. It's similar to the KPZ, but you see here the 4 to 1 scaling of the Edwards-Wilkinson. Of course, we lost one scaling because correlation is invariant under linear functions. We proved this result also for other models in the class, for example, the semi-discrete equation and some Ginzburg-Landau models. Since this is already scaling invariant, so we have the space-time correlation function already invariance here, and we can write it down also in terms of the variances only, so you see it here. And here we have actually an explicit expression for the variances. So we have an explicit expression for the covariance function. It's interesting to compare that to the KPZ. Okay, so we saw aging for stationary KPZ and Edwards-Wilkinson models with explicit aging functions, these ones, for various models, right? For various models in the class. And it's interesting to see if you can prove that for other models in the class, for example, asymmetric Ginzburg-Landau and the parabolic Anderson model. Also, another interesting question is, you remember our result on the Cornelior model. We took n to infinity first, then t to infinity. It is interesting to take them together to infinity in some way and to see what happens. There is a recent progress in the two-dimensional stationary KPZ, and aging is expected there as well in the logarithmic time scale. This is also a nice question. And in higher dimensions, as I mentioned, the parabolic Anderson model in the Dembo-Deutschel paper. So there, aging is expected if you take the logarithm for beta large, okay, in the subcritical temperature regime. Okay, thank you very much for your attention, and please don't hesitate to contact me if you have any questions or remarks.